barely. It's almost May. It's almost May. I saw her in the class. I haven't seen her. No, it's actually pretty random too.
Yeah, we're like.
All right, they've finally put me on medication. If you want to hear today's lecture and cannot hear it from where you're sitting, I do advise you to move closer to the front of the row. This is the maximum volume I think I can maintain. So I'm switching things up a little bit. I'm going to prove the geometric series formula today with the boring proof. I do not feel up for the exciting proof. I will need 2 volunteers for the exciting proof on Monday through playing a basketball game. Do I have 2 volunteers for Monday? All right, you 2 are it. And you both have 1 homework exemption problem for the rest of the semester. Always good to volunteer for things. Okay, so the goal today is to talk a little bit about sequences and series, to talk about some convergence problems, to talk about how can we determine when something converges, and then an even harder problem, how can we determine what it converges to. So the first is an example. So let's let an be n squared minus n to the 3 halves plus 4 log of n over n cubed. So there are lots of different ways of determining whether or not this sequence converges. So the 2 most common ways are through factoring and through L'Hopital's rule. So by factoring, the first thing we do is we look and see what's the largest power of n in the numerator. It's n squared. What's the largest power of n in the denominator? It's n cubed. Let's pull those out. And so this looks like n squared 1 minus 1 over n to the half plus 4 log n over n squared divided by n cubed. As n goes to infinity, this term over here goes to just 1. 1 over square root of n goes to 0. Log n over n squared goes to 0. The denominator is going to look like n cubed. We have n squared over n cubed. So this is going to look like 1 over n times 1 minus 1 over n to the 1 half plus 4 log n over n squared. And so the limit as n goes to infinity of an will just be 0. Now in this analysis, I'm assuming that you know that the log of n over n squared goes to 0. If you didn't know that fact, how could we prove that the log of n over n squared goes to 0? I have very little voice. I need participation today. What could we do to prove log of n over n squared goes to 0? Not integrate. So whose rule gets us this limit by differentiation? L'Hopital. So the limit as n goes to infinity of the log of n over n squared is the limit as n goes to infinity of 1 over n divided by 2n. And the reason is we can use L'Hopital's rule whenever we have infinity over infinity or 0 over 0. And this is just going to be the same as the limit as n goes to infinity of 1 over 2n squared, which is just 0. Okay, so this is one way to show that the terms a n tend to 0. Another way is to just do L'Hopital directly. So the limit as n goes to infinity of an, well, we have infinity over infinity, so let's use L'Hopital's rule. So we have, this is the same as limit as n goes to infinity of 2n minus 3 halves n to the 1/2 plus 4 times 1 over n divided by 3n squared. So now what do we do? Can we evaluate this limit, or do we need to do something else? So what does this limit look like? What does the top look like? As n goes to infinity, what does the numerator look like? The numerator looks like 0? Why 0? I agree, this term looks like 0, but the whole numerator, what does the whole numerator look like? Infinity. What does the denominator look like? So what should we do? L'Hopital again. So we apply L'Hopital again. Now we'll get 2 minus 3/4 1 over n to the half minus 4 1 over n squared. Now as n goes to infinity, what does the numerator look like now? 2. And what does the denominator look like? So can we use L'Hopital again? We can only use L'Hopital when we have 0 over 0, infinity over infinity. But we're quite happy not to have to use L'Hopital, right? That means we finally finished the problem. We have 2 over infinity, so this limit is just 0. So these are two different ways of calculating what is the limit of the sequence an. All right, so the next topic is series. And these are sums of terms in a sequence. So given a sequence an, n goes from 0 to infinity, the associated series is Sn equals the sum k goes from 1 to n of an. So I guess I'm doing it from 0. So a0 plus a1 plus an. So it's the sum all the way up to the nth term of the sequence. And when we get to Taylor series, we'll have a lot of stuff like this. And the question is going to be, does the series converge? And if so, what does the series converge to? So the first fact, we need an to go to what for the series to converge? So what do you think an has to go to for the series to have a chance to converge? 0. So imagine an doesn't go to 0. Well, there are several ways it could not go to 0. Maybe it converges to another number like 1. Well, if an is converging to 1, then the series is going to be getting larger and larger and larger by essentially 1 every single time. What if an doesn't go to 0? What if it oscillates between +1 and -1? Then you're going to get large jumps when you look at the series. So the only way the series can converge is if the individual terms are going to 0. If the individual terms are not going to 0, well, that could be maybe infinitely often you have a term that's greater than a half. Well, then if the series were converging, I shouldn't be able to jump by a half by adding a term. So for this series to converge, I need the individual terms to go to 0. So we have this implication. What about the other direction? If the individual terms go to 0, does that force the series to converge? So does an go to 0 force Sn to converge? So we know that this is necessary. It's necessary that an goes to 0 for the series to converge. Is it sufficient? What do you think? So if an going to 0, if that's going to cause trouble, it's going to come down to like how quickly an is going to 0. So what do you think might give us some trouble for the series to converge? If a(n) is going to 0, how? Do you think it's a question of a(n) going to 0 quickly, slowly? What do you think is going to cause us trouble? So let's say we have things like 1, 1/10th, 100th, 1,000th, 1,000,000th, 1,000,000,000th. Should that converge? So if the a(n)s are going to 0 very rapidly, that should force convergence. What about if the a(n)s are going to 0 very slowly? That could be where the trouble is. And in fact, it turns out that the answer here is no. So it is necessary, but not sufficient. So the question becomes, can you give me a sequence of numbers such that the terms tend to 0, but the series does not converge? So this, I know at least one of these examples is in the reading. So what's a sequence of positive numbers that tend to 0, but the sum does not converge, even though the individual terms are getting smaller and smaller and smaller? Yes? The harmonic series. So I'm going to hold off on the harmonics for a moment and do an easier example, and then we'll get to the harmonics. So 1, my voice is sore. Somebody tell me the next few terms. So a couple announcements for today. Somebody had asked me to do an independent study on sabermetrics next spring. So the sports lunch today will be talking about, among other things, the possibility of an independent study in mathematics and sports. All right, what's the next few terms? There we go. So this should be pretty clear that this series is going to diverge. And so if we look, the sum of these two terms is 1, the sum of these 3 is 1, these 4 is 1, these 5 is 1. So the series is going to diverge. It's going to diverge very, very slowly. But the terms are tending to 0, and the sum blows up. So another example is the harmonic series. So here, a(n) is 1 over n. And there is a reason I want to go this far out. Okay, I'm going to show you that the harmonic series diverges. How large is a third plus a fourth? No? 7/12, and 7/12 is greater than 1/2. I don't care what the sum of these 4 terms are. The sum of these 4 terms is greater than 1/2. Because if I had 1/8 4 times, that would be 1/2. I have 4 numbers. Each number is greater than or equal to 1/8. So the sum of those 4 numbers is at least 1/2. And now you can see why I went all the way down to 16. What's the sum of those terms? It's at least 1/2. So we'll see another way of proving that the harmonic series diverges by doing what's called the integral test. But this is a really nice elementary way to see that the harmonic series diverges. And it all comes down to clever ways of grouping things. And so while this sum diverges, it diverges extremely slowly. Okay? So what I want to do now is I want to tweak the harmonic series. And so this is called the alternating series. So an is -1 to the n plus 1 divided by n. So it's 1 minus a half, a third, minus a fourth, a fifth, minus a sixth, dot, dot, dot. If I didn't have the minus signs, then it would clearly diverge. But the minus signs means there's going to be a lot of cancellation. So the question is, do I have enough cancellation so that it's going to converge? So let's start looking at the first few terms in the series. So S1 is just the sum of the first term, that's just 1. S2 is the sum of the first two terms, which is 1/2. There's a reason I want to write the odds up top and the evens below. If I sum the first three terms, I have a half plus a third, which is 5/6. Thank you. If I sum the first four terms, I have 5/6 minus a fourth. All right, so that's going to be 20 minus 6 is 14/24. The pattern may not be clear now, so let's just do it for two more terms. S5 is I take 14/24 and I add a fifth. 5 times 14 is 70, plus 24 is 94, I believe, 120ths. And then I have to subtract off 1/6. I multiply by 20, and that should become 74 1/20ths. All right, so let's look at these numbers. Do you notice anything about the odds or the evens? Yes?
The odds diverge to 1, the evens converge to half.
All right, so you're conjecturing that the odds converge to what?
1?
I don't think they could.
Well, roughly.
Well, the odds start off at 1,
Oh, but actually.
and the evens start off at a half. So I think your conjecture, okay, so the odds and evens are getting closer. What other patterns do you notice? Yes?
The odds are decreasing.
Good. The odds are decreasing, and the evens are increasing. So if I multiply 24 by 5, I get 120. 14 times 5 is 70. This is 74. The evens are increasing, the odds are decreasing. It turns out that we can prove both of these things, that the odds will always be decreasing and the evens will always be increasing. Let's go from S1 to S3. Well, to get from S1 to S3, I have to add these next two terms. This term is negative, this term is positive. Since the negative term is first, I subtract off more than I add. So S3 has to be less than S1. Similarly, when I get to S5, I subtracted a quarter and I added a fifth. So the odd terms are decreasing. A similar argument gives you that the even terms are increasing. Okay? Now the other thing which was noticed is that the odds and the evens are getting closer to each other. How far apart are the odds and the evens? Well, Sn minus Sn minus 1 is 1 over n. Right? The difference between the odds and the evens is just one more term. And the nth term is just of size 1 over n. So the difference between the odds and the evens is going to get very, very small. The odds are going down, the evens are going up, the distance between them is getting to 0. So it's going to look something like this. Here's my odds. Here's my evens. They have to approach a common value. Anybody have any idea of what that common value is? I'm sorry?
No, it's not 3/4.
It's not 3/4. So how do you know it's not 3/4? Yeah, see, if this was 90 over 120, that's 3/4. So 3/4 is still in the game. I'd have to go one more term, I think, to see that 3/4 fails. When we get to Taylor series, we'll see that this is actually converging to the log of 2. And again, whenever I write log, I always mean base e. And that's about 0.69, just to get some rough idea. A very important number. Okay. So this gives you, an idea of some of the analysis you can do. It can get, a little complicated, break it up into cases, try to get a sense of what's going on, look for patterns. And that's where sequences and series can become difficult, is trying to figure out exactly what is the pattern, what can you exploit in your analysis. Now the question, of course, is why do we care about stuff like this? There's often going to be some physical process that we care about, and the different terms in the sequence will be the different effects. And we might want to sum all of them up and get some idea of what's going on. Or we might have a very complicated function, and the hope might be that by just taking a few terms, we can get a pretty good approximation to the function. And we want to know exactly how good is our approximation. Okay, so it's time now to do the geometric series. I will unfortunately save the interesting proof of the geometric series till Monday's class. So I will do the standard boring proof. How many of you have seen the geometric series before? Okay, not that many. So geometric series. So an is r to the n. So Sn is 1 plus r squared plus r cubed plus dot dot r plus r to the n minus 1 plus r to the n. So here's the boring proof of the geometric series formula. If I multiply this by r, what do I get? So should I write the r right here? The whole proof comes from writing r in a clever spot. I'm going to write the first term down here underneath the r, then r squared, r to the n minus 1. R to the n minus 1 times r is r to the n. R to the n times r is r to the n plus 1. Now what should I do? So what should I do now? Subtract. And if I subtract, I'll have this massive cancellation, and the only things that will survive is the stuff at the very end. This is very similar to the proof of the fundamental theorem of calculus, when we had these telescoping sums, using the antiderivative, and only the end terms survived and got f of 1 minus f of 0. If I subtract here, I'll just be left with 1 and r to the n plus 1. So we're seeing a lot of things now that arose in calculus. Over here, where I had two different things, one going down, one going up, converging to a common value, this was like the upper and the lower sums. So a lot of the things we've seen in calculus actually are sequences and series just lurking in the background. So if we subtract, we get 1 minus r times Sn is 1 minus r to the n plus 1. Well, that's just the same then as Sn is 1 minus r to the n plus 1 divided by 1 minus r. And so here's the formula for Sn. And then we might be interested in the entire sum. So how many of you have taken economics in economics class? Yeah, they might talk about like the multiplier effect. So if you're doing the multiplier effect, you would have geometric series here, and you'd want to know in the limit what would be the effect of something like that. So the limit, as n goes to infinity of Sn, would be the sum n goes from 0 to infinity of r to the n, is 1 over 1 minus r if the absolute value of r is less than 1. So as long as the absolute value of r is less than 1, we can take the limit without any trouble. Imagine r is something like 1/2. Well, then if I take 1/2 to a higher and higher power, it's getting smaller and smaller and smaller. And so this expression, if I wanted to, I could write this expression as 1 over 1 minus r minus 1 over 1 minus r times r to the n plus 1. And you can see now as n gets very, very large, this piece here becomes negligible. And it's going to converge to just 1 over 1 minus r. So let's do an example. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 what would that equal? So what would this sum equal? 2. So this is a geometric series. R equals 1/2. Therefore, the sum is 1 over 1 minus 1/2, which is 2. All right. What about 1 plus 2 plus 4 plus 8 plus 16 plus 32? So is this correct? The sum of all the powers of 2 is -1. It gets so large, it goes all the way past positive infinity, comes back through negative infinity, and almost makes it back to 0. Okay, this is absurd, right? I should not get a negative number from summing positive numbers, right? So you want to have some intuition when you're looking at mathematical expressions. Something has to be wrong here. What's wrong? Yes?
I should be less than 1.
Yeah. No. Cannot use as the absolute value of r is greater than 1. So again, whenever you're using a mathematical result, you always have to check your conditions and see, do you satisfy the conditions of the theorem? And for this example, the answer is no. You know, I can't use the geometric series formula unless the absolute value of r is less than 1. And since the absolute value was 2, which is much greater than 1, you know, it's absurd to try to use it there. Okay. So it turns out we have a lot of really good tests as to whether or not a sequence converges, a series converges. A lot of them involve comparing a series to a very special geometric series. It's often difficult to figure out exactly what to compare it to. So in the notes, which you've all read many times by now, you've read about the root test and the ratio test. And what's really going on there is the root and the ratio test are doing a comparison in the background, but without forcing you to be explicit and say, what are you comparing it to? But frequently there is a geometric series that's lurking for the comparison. And we'll talk more about this on Monday. So what I want to do now is I want to talk about the comparison test. Bless you. So in some sense, this is one of the most difficult of the tests as to whether or not something converges to use, because you have to figure out what to compare to. So assume the absolute value of an is less than or equal to bn, and the sum, n goes from 1 to infinity, of bn converges. Then the sum, n goes from 1 to infinity, of an converges. So this is very useful. I can tell if a series converges by comparing it to a series that I know converges. So if I can find some series so that term by term I'm less in absolute value, then I must converge. Now unfortunately this doesn't give you some information that you would love to have. What would you love to know? So I tell you it converges, but there's something else you might want to know. Not the sign, yes. We don't know what it converges to, right? You know, if somebody tells you, there is an optimal strategy so that you will, win the contest. I don't know what it is, but there's an optimal strategy for you. Well, that's not so useful. It's good to know at least that an optimal strategy exists, but you'd like to know how to find it. So it's going to be very difficult to figure out what the series converges to. We saw this with the alternating harmonic series, where that converges to the log, base e of 2. We could show it converges, but to figure out that it converges to the log of 2, that's much harder. So let me sketch the proof. So we know negative bn is less than or equal to an is less than or equal to bn, because the absolute value of an is at most bn. So if we sum then we know that the sum of an lies somewhere between minus the sum of bn and positive the sum of bn. This converges. This converges. We'd love to conclude that the sum in the middle converges as well. The problem is, what if it oscillates? And so to prove that it converges, we have to be a little bit more careful. And we have to use the fact that that each an is between minus bn and bn. What do you know must be true about bn as n goes to infinity? Converges to what? It converges to, so we know that bn's are converging to 0, so the an's are going to converge to 0. What we're going to show is that if we truncate this sum, then the sum of the remaining terms is as small as we wish. Depending on how small you want it to be, that will affect where we truncate. And that's going to then allow us to prove that the sum of an converges. So the technical proof would be the following. Since the sum of bn converges, given any epsilon greater than 0, there is a n0 such that whenever n is greater than or equal to n0, we have the sum, n goes from n to infinity, of bn is less than epsilon. It's also less than infinity, but that's not that surprising. So why is this true? This is essentially what it means for a series to converge. So what I'm saying is that from some point onward, all the remaining terms add a negligibly small amount. If this wasn't the case, I couldn't converge. So if I'm converging, if I'm getting closer and closer to my limit L, then the amount of movement from all the remaining terms has to be insignificant. So because bn converges, you give me any tolerance. I want to be within 1/10, 1/100th, 1,000th, 1/1,000,000th of the limit. Sure. You tell me how close you want to be, and I'll tell you what n I have to take, so that as long as I'm taking terms from that height and further, I can't move by more than epsilon. So here, you tell me an epsilon, that will give me an n0. Not surprisingly, the smaller epsilon is, what do you think happens to n0? As epsilon gets smaller, what do you think happens to n0? It gets bigger, right? Because I want this sum to be at most epsilon. Well, as epsilon gets smaller, I have to go further and further down in my sum because my terms are getting smaller. I need to go so far down that the sum is less than epsilon. The smaller you make this, the fewer terms I can have. I've got to push myself further down. How does this help us? Well, the sum, n goes from 1 to infinity of an, is the sum, n goes from 1 to n minus 1 of an, plus the sum, n goes from n to infinity of an. And this is, at most, epsilon in absolute value. So why is this at most epsilon in absolute value? Well, each an is at most bn in absolute value. The an's could have different signs. Some of the an's may be positive, some of the an's may be negative. How can I make this as large as possible? I don't want to have any cancellation because of signs. Right? If the an's alternate, then I can have some cancellation. So the worst possible case is if all the an's are positive. Okay? And I know each an is at most bn, so the worst possible case is not only are they all positive, but each an is bn. And we know that the sum of bn from this point onward is at most epsilon, so the sum of these is at most epsilon. So this is what is essentially going to allow me to prove that the sum of an converges, is the difference between this infinite sum and this finite sum can be made as small as you want. If you take a real analysis class, they'll go into a little bit more detail about all this. This is enough to give you, I hope, a flavor of how these analysis proofs go. All right, so this is the comparison test. The next one is the squeeze theorem. And so you've seen a version of this with some limit problems. And so now, let an be less than or equal to bn less than or equal to cn. if the sum n goes from 1 to infinity of an and the sum n goes from 1 to infinity of Cn converge, then the sum n goes from 1 to infinity of Bn converges. So I'm not going to go through the proof of this. Even if I had my voice, I would not go through the proof of this. But I claim we've already done a special case of the squeeze theorem. Yes?
Didn't we just do it there where like C and A are equal?
Yeah, almost equal. You have to tweak it ever so slightly. Yes. So note if an equals negative Cn, have the comparison test. And that's why I'm not really doing the proof again, because it's essentially the comparison test again. And because these series converge, an has to go to 0, Cn has to go to 0, the bn's are going to go to 0, good. It makes sense, bn has a chance of having a convergent sum. And now it's essentially the same proof as the comparison test. Okay, so this gives you ways to prove if a series converges. If you can somehow compare it to a series that converges, as long as it's less term by term by term and an absolute value, it's at most, you win. So the reason these are some of the hardest problems in Math 105 is that you have to figure out what to compare it to. If I give you a function to take derivatives of, you just keep using your rules of differentiation to make it simpler, 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 just keep knocking it down. Integration is hard, because I can easily give you something that cannot be integrated in closed form. When you have double integrals, this can be a little bit hard because there's, it may not work out nicely, but you at least have a few different tricks to try. Let me try switching orders of integration. Let me try changing variables. Hopefully, one of these things will work. For sequences and series now, if I want to try to prove a series converges by the comparison test, I have to figure out what to compare it to. And that's the difficulty, is it's not always clear what to compare it to. The whole point of the ratio and the root test is to do a little bit more algebra, but have somehow the ratio and the root test figure out exactly what series to compare it to. So as an example, imagine an is 1 over 4 to the n minus 3 to the n. So does the sum, when you go from 1 to infinity, of 1 over 4 to the n minus 3 to the n converge? So what do you think? Converge or diverge? Or if I change the denominator a little bit, what would make this problem a lot easier? How could I change the denominator? What's something close to this, where I would know immediately if it converges or diverges? So instead of giving you 4 to the n minus 3 to the n, what could I give you where you could immediately look at this and say, oh yes, this converges because 1 over 4 to the n. So if I just gave you 1 over 4 to the n, why does that converge? So why would 1 over 4 to the n converge? Yes?
As n goes to infinity, that becomes 0.
Well, it's not enough for individual terms to go to 0. Why does 1 over 4 to the n converge? It's a geometric series where r equals 1/4. So if I just gave you 1 over 4 to the n, it would converge. It's a geometric series. Unfortunately, I gave you 1 over 4 to the n minus 3 to the n. As n is really large, approximately what is 4 to the n minus 3 to the n? So if n is huge, approximately how big is 4 to the n minus 3 to the n? I'm sorry? No, I'm not talking about the reciprocal. I'm just talking 4 to the n minus 3 to the n. Yes?
0?
No, I'm looking at 4 to the n minus 3 to the n. If n is huge, 4 to the n minus 3 to the n is approximately what? So you have to be a little bit more careful. You have to quantify which infinity. Does it look like 5 to the n? Does it look like 2 to the n? What does 4 to the n minus 3 to the n look like?
1 to the n.
Not 1 to the n. 4 to the n minus 3 to the n is not 4 minus 3 to the n. This is my favorite example. Consider the US debt, okay, about 16 trillion, right? We're now going to require all politicians to pay for their alcohol. This is a sizable amount of money, but will you notice the difference? It's completely dwarfed by the debt. 4 to the n completely dwarfs 3 to the n when things are large. This is growing much, much faster than 3 to the n. If n is huge, the denominator looks essentially like 4 to the n. You really don't see the 3 to the n. So morally, this looks like 1 over 4 to the n. You would expect it to converge. So we want to do a comparison test. So let's compare 1 over 4 to the n minus 3 to the n. What would you like to compare this to? 1 over 4 to the n. And so if this were true, we could then use the comparison test. This converges because it's a geometric series, so therefore this converges. What's the problem with this inequality?
The lower bound?
I'm sorry?
There's no lower bound.
Not quite.
It's not equal. Equal to? I mean, isn't it? Well, you have an equal percent. Or less than equal to.
I have the wrong sign. Which way does the inequality go? It goes the other way. The problem with this inequality is false, right? The denominator here is smaller than here, so this number is larger than this number. This inequality has no chance of working. So while I would love to compare this to 1 over 4 to the n, I can't. It won't work. So the question is, what should I compare it to? So if I take a series, if I take a sequence, if I rescale all the terms by 5, does that change whether or not it converges or diverges? No. It'll change what it converges to by a factor of 5. If I change every term by multiplying by 3, it doesn't change whether or not it converges, it just changes what it converges to. So instead of comparing this to 1 over 4 to the n, I should compare it to, what do you think? Sorry?
1 over 5 to the n.
Well, if I take 1 over 5 to the n, that's going to be even worse because 5 to the n is going to be smaller than this. So I want to rescale this. I want to multiply this by something. What should I multiply this by? And if you don't know exactly what number, just put in. So if you're not sure what number to use an arbitrary constant. Let's put in some number c. And let's see, can we find a number c such that this is true? If we can, then we can use the comparison test. So the whole idea is we looked at this and we saw, well, the denominator looks roughly like 1 over 4 to the n. When n is large, it's essentially 1 over 4 to the n. All I have to do is compare this to 1 over 4 to the n. Unfortunately, the comparison goes the wrong way. I need this to be larger than this. And then the sum of this being converging would mean the sum of that converges. So sadly, it goes the wrong way. But hey, if I rescale this, I should be okay. What should I rescale it by? If I put in 1,000,000, I'd probably be fine. But I can't just look at this and see exactly what to put in. So let's put in some number c and try to figure out what c do I need to take. So I want this to hold. So this means we need 4 to the n to be less than or equal to c times 4 to the n minus 3 to the n. So we need c times 3 to the n to be less than or equal to c minus 1 times 4 to the n. So we need c over c minus 1 to be less than 4/3 to the n. Now what's nice is 4/3 is greater than 1. So if this is satisfied for n equals 1, then it's satisfied for n equals 2, n equals 3, n equals 4. So enough to find c so that c over c minus 1 is less than or equal to 4/3. Because if it's less than or equal to 4/3, it's less than or equal to 4/3 squared, 4/3 cubed, 4/3 to the 4th. Can anybody give me a value of c that works? Anything over 4. So if we take c equals 4, we win. So here's something interesting. What if we took c equals 1/2? We would get 1/2 over 1 minus a half. What does that equal? Nope. I'm sorry, it equals 1, which is less than or equal to 4/3. Oh, I'm sorry. I was the wrong way, sorry. It's 1/2 minus 1, so we'd get -1, which is less than 4/3. Wait a minute, but if I take c equals 1/2, this wasn't less than or equal to 1 over 4 to the n. If it's not less than or equal to 1 over 4 to the n, it's clearly not going to be less than or equal to 1/2 times 1 over 4 to the n. So something is wrong. When we look at this, what's the minimum value of c? We know c has to be at least how large? C has to be at least 1. So the question is, what went wrong? If I take c equals 1/2, this inequality is satisfied. This is one of the most common algebra mistakes people make.
The series starts at 1.
I'm sorry?
The series starts at 1.
That's okay. So you get 1 over 4 minus 3, which is 1 over 1. That's fine. Very, very subtle. Yes? Excellent. Excellent. When we divide it by c minus 1, if c is less than 1, we switch the inequality because we've divided by a negative number. You've got to be very, very careful with algebra. Okay? And unfortunately, we're going to be at the point where the amount of Calc 3 is minimal. It's going to become algebra again. You have to be careful about something like this. So over here, if we know that c has to be at least 1, then when we get over here, we would know not to do anything foolish like taking c equals 1/2. But you need to have some feel of the numbers you're manipulating. Otherwise, you could get to this point, you might take c equals 1/2. Now, of course, once you have this, you can always go back and check and make sure, does this work? And so if you take c equals 4, a little bit of algebra will show you that, yes, this inequality is always satisfied. And so c equals 4, we now have 1 over 4 to the n minus 3 to the n is less than or equal to 4 over 4 to the n. So the sum of 1 over 4 to the n minus 3 to the n is less than or equal to the sum of 4 over 4 to the n, which converges. And so we win, and we're able to show that the series converges. So what I hope you get from this is the difficulty in using the comparison test. It wasn't so bad, if you look at it long enough to see that we want to compare it to something like 1 over 4 to the n. But then you had to figure out exactly what to compare it to. And hopefully by seeing the pain of this, you will appreciate the ratio and the root test. Okay? They're a little bit more algebraically intense, but it's very methodical. Is the quadratic formula pleasant? No. You've got square roots and all that stuff. But is the quadratic formula difficult? It's this black box algorithmic procedure. Step by step by step, you know exactly what to do. If you just follow the steps, you will get the answer. The ratio and the root test are like that. Sometimes you have to do a little bit of work and be a little bit clever in terms of how to arrange the algebra, but for the most part, the ratio and the root test are very straightforward. They're essentially doing the comparison test, but they're figuring out what to compare it to, and they're keeping that under the radar. All right, so what I thought I would do for the last few minutes is just if there were questions from the third midterm, I thought we would just spend a few minutes talking about them. So are there any problems that people would like to see? If you haven't picked up your exam, by all means, go and grab it. Okay. So any problems people want to see? Yes?
Yeah, can you do 5, please?
Sure. Does it start off with minus y or y? Which way is it? What is it? Okay, it's y minus? Okay. Okay. So I tell you that the function is 3 times continuously differentiable. And one of the theorems we have is if the function is twice continuously differentiable, then it doesn't matter which order you differentiate. So over here, this is the derivative of f with respect to x. This is the derivative of f with respect to y. Since my function is 3 times continuously differentiable, it's also twice continuously differentiable. If I take the derivative of this with respect to y, and I take the derivative of this with respect to x, I should get the same number. Well, if I take the derivative of this with respect to y, I get 1 minus derivative of sine is cosine x plus y. And over here, I get minus 1 minus cosine of x plus y. So not surprisingly, Cameron Kayla's calculus knowledge is a little lacking. Okay? This is, I think, the simplest way to see that they can't be right. There's another way that a lot of people tried, is they tried to say, well, look, if this is the derivative of f with respect to x, let's integrate this. And if this is the derivative of f with respect to y, let's integrate that, and let's see if they're the same. So we would have df dx is equal to y minus the sine of x plus y. If we integrate both sides with respect to x, we get f of xy minus plus cosine of x plus y plus what? It's not just c. It's some constant. But remember, when I integrate this, whatever function this is, when I differentiate with respect to x, I have to get back to this. It's not just c. It can be any function of y. Because any function of y, when I differentiate with respect to x, I will get back to this. And similarly, if I look at the integral of df dy with respect to y, I would get negative xy plus cosine x plus y plus c2 of x. And then there's no choice of c1 and c2 such that these are equal. They have the same cosine term, that's great. They differ by a 2xy. And I can't get this to become 2xy. I can only have this become 2y. So you could do it by integrating, but you have to be careful that if you're integrating, this arbitrary constant is allowed to depend on y. Because again, the whole idea of a partial derivative is you keep every other variable constant. All right, we might have time for one more. Nope. Okay. If people want to stay and ask another one, that's fine. But